Hello and welcome to the presentation on Chapter 8 of the International Levee Handbook. We are Guillaume Veylon from Irstea and Edouard Durand from CETE, France, and we were the lead authors for this chapter of the handbook. In this short presentation, we will try to give you just a flavor of the content of the chapter by way of an introduction to some of its aspects. Levee assessment and design require multidisciplinary engineering approaches because geotechnical and hydraulic issues are intimately linked and interact very strongly. Given that designers and engineers are often specialized in one discipline, levee projects require integrated management. For example, after the selection of the levee alignment and geometry, see chapters 7 and 9, failure scenarios are established based on chapters 3 and 5, and representative design situations are defined for all stages of construction and life of the levee, see chapter 9 and 10. Chapter 8 is a toolbox which details the morphological, hydraulic, and geotechnical analysis tools needed to assess the performance of a levee. For the purpose of levee assessment and design, Chapters 8 needs inputs from other complementary chapters, especially from chapters 7 and 9. This slide aims to illustrate the links between these chapters on a simplified example of stability analysis. Chapter 7 provides methods to determine the characteristic values of loadings and actions applied on the levees, for example, characteristic water levels Z, Y, K, and also the nature of soil from which levees are formed and founded. For example, here, the characteristic values of cohesion, CK, and international friction angle, phi K. The outputs of this chapter are the characteristic values of morphological, hydraulic, and geotechnical data necessary to establish accurate modeling results. The information provided by Chapter 9 are used to define first the design situations, for example, design water level corresponding to a given return period, and local scour depth. And secondly, the partial factors to be applied to the characteristic values of actions and geotechnical parameters, here gamma C and gamma phi. The Chapter 8 details several actual methods to analyze various physical processes and failure modes. For example, we determine the phreatic line from seepage analysis and then evaluate the factor of safety from the slope stability analysis. Chapter 8 is divided into 10 subsections following source pathway receptor logic. Sections 8.2 and 8.3 deal with the water-levee interaction processes occurring outside the levee, generally related to waves and currents, and also inside the levee in order to evaluate the internal flows and gradients. Sections 8.4 to 8.9 give tools to assess the structural performance of the levee regarding the physical processes which can lead to the levee deterioration or failure. The tools and methods for functional performance and post-failure analysis, that is to say for breach and inundation modeling, are described in sections 8.10 and 8.11. I am now going to give the floor to Edouard, which will talk to you about hydraulic processes and structural performance regarding external and internal erosion.
Subsection 8.2 concerns external hydraulic processes. It details successively processes related to wave action, then overflow, and finally score in a river channel, but also of beaches in front of coastal levees. For each main process, governing parameters are given, and up-to-date methods and formula are described with their application domains and limits. Therefore, we can find in this subsection how to evaluate wave reflection, wave run-up and run-down, wave overtopping upon levees or flood walls. For overflow, the way to evaluate discharge is given in several cases, and a specific section is devoted to spillways of levee embankments. On this slide, we can see an example of a specific formula to evaluate the run-up height exceeded by 2% of incoming waves according to recent Eurotop method. Subsection 8.2 also gives elements related to levee slope resistance according to overflow discharge. In score paragraphs, methods to evaluate score in river channel with geometry and river geomorphology are detailed, but the case of score at beaches and waves effects are also treated. The aim of subsection 8.3 is to introduce internal hydraulic processes as mechanisms responsible of internal pore pressure and flow inside levees and their foundations. Therefore, methods and formula related to seepage analysis, wave-induced or consolidation-induced pore pressure are detailed. For seepage analysis, methodology to define phreatic, flow, and equipotential lines are given for a stationary state. So, attention of the designers are required on several issues as permeability, anisotropy, as shown on the slide, hydraulic condition, permanent or transient state, that determine levee and foundation saturation, internal flow, and exit gradients. In wave pore pressure induced paragraph, elements about elastic and plastic strain and their effect on pore pressure are discussed, and formula to obtain specific time scale are given. An example is also treated in a specific box. The effect of consolidation on pore pressure is reminded, and the way to express pore pressure ratio, or U, is detailed. Then, the external erosion subsection 8.4 method for assessing the effect of currents and waves on the levee structure are described, and limited guidance measures to protect against those effects are provided. Indeed, levees' integrity and long-term stability are dependent to external hydraulic interaction between structures and various hydraulic loadings, described previously in 8.2 subsection. Therefore, critical concept for erosion, critical velocity concept, critical shear stress concept are first of all introduced, and prominent strengths or resistance variables with regard to soil stability are given, such particle size, relative buoyant density, etc. Then several protection revetments or systems against currents, waves, or ice are detailed. Some formula and guidance are given for each of the systems, what enables designer to propose appropriated levee revetments or protection systems against external hydraulic loads. For example, concerning critical velocity concepts, research results of Brio and Hell describing critical shear stress versus main grain size of particles are given in the principal subsection 8.4.1. For grass resistance under wave overtopping, we can find in 842 grasp performance curves under overflow conditions, but also grasp erosion curves under wave impact for different wave heights, as shown in the graphic presented at the bottom of the slide. In this section, the basic internal erosion mechanisms are presented related to US Code 2012. It means there is backward erosion, concentrated leak erosion, suffusion, and contact erosion. First, a description of the general hydraulic and geometric conditions for internal erosion initiation and development are described. The successive phases of the internal erosion scenario from the initiation to the breach are briefly introduced. For each erosion mechanism, the models and criteria to be used for the assessment of the different internal erosion mechanisms are given. The last section deals with the special issue of the stability of granular and geotextile filters. For a suffusion mechanism, the synthesized geometrical condition proposed by Lee and Fana 2008 on the basis of the KD and Kenya law criteria are presented. The hydromechanical criterion proposed by Lee and defined as a function of the Terzaghi critical gradient is also given. I'm now going to give back the floor to Guillaume. He will talk to you about the geotechnical analysis tools.
The slope stability section starts with an overview of the common failure surface geometries, planar, circular, etc. The 2D approximation is discussed and the conditions for an accurate slope stability analysis are reviewed. The slope stability methods are presented from the simplest to the most refined in order to be useful at each step of the design process. Simplified methods are presented, for example, at-rest pressure approach, bearing capacity approach, and design charts are also given. Limit equilibrium methods, which are still the most used methods in practice, are detailed. Analytical methods like infinite slope model, Swedish method, slice methods such as Fellenius, Bishop, Spencer, Morgenstern, Price, Jambu, etc. and perturbation methods are also described, and their equivalence with the slice methods is discussed. Limit analysis methods is also briefly reviewed. Its principles and main assumptions as regards to the previous approaches are discussed. Concerning the stress deformation analysis method, the ILH provides a review of the different families of stress-strain soil models and a discussion about the issue of evaluation of a factor of safety from these analyses. For example, the feasibility study proposes a procedure for evaluation of the factor of safety from the Jambu charts is detailed. From a general point of view, each method is described in terms of its main assumption and when needed, the general analytical framework is presented. The limitations associated with the different approaches are discussed and recommendations for their use are proposed. The settlement section deals with the settlement analysis issues during levee design or construction processes. It presents the most commonly used method to evaluate settlement of a compressible soil layer. The settlement analysis is developed within the framework of unidimensional consolidation. Verification of settlement prediction is based on the Asaoka method. Finite element methods are referred to as complementary methods when the unidimensional assumption is no longer valid. However, it is underlined that this approach necessitates the use of complex input data, which are not always easy to collect. Within the unidimensional consolidation framework, settlement is decomposed in instantaneous settlement, primary settlement, which corresponds to the consolidation phase, secondary settlement, which corresponds to creep, and a corrective term accounting for irreversible lateral movements. The formula for each term is given. It is reminded that the input parameters should be determined from laboratory tests. See Chapter 7. The seismic analysis section first details the two critical design issues when evaluating the seismic performance of a levee: evolution of material strength and stiffness, and evaluation of permanent post-earthquake deformations. As a preamble to the presentation of the seismic analysis methods, the principles for determining seismic action and soil properties are reviewed. The types of methods for stability and permanent displacement analysis of levees subjected to dynamics loading are reviewed. Pseudostatic approaches, where seismic loading is modeled as an additive static inertial force, and pseudodynamic methods, including sliding block analysis, like the Newmark method, and simplified methods like Ambrasé-Menu and Magdisi-Seed methods, but also the more recent approaches developed by Gray and Travasarou and Swaisgood are described. The dynamic stress deformation analysis are only mentioned and some references are given. Concerning earthquake-induced liquefaction, the physical processes are described in detail. Definitions of flow liquefaction and cyclic mobility are given, and the distinction is made between susceptibility to liquefaction and liquefaction potential. The governing parameters are reviewed: particle size of the soil, saturation condition, density, age, loading mode, soil microstructure, etc. And the liquefaction susceptibility criteria for sands and fine-grained soil are explicited. The simplified procedure based on the work of Idris, Seed, Boulanger, Stocco, etc. for the evaluation of soil resistance to liquefaction from in-situ tests like standard penetration test and cone penetration test is described in detail. The section 8.9 is specific to flood walls stability, as they are structures associated to the levee. The flood walls needed to have their own section as they are part of the flood protection system, but have specific failure modes. The first part of the section deals with the evaluation of hydraulic forces acting on the flood walls. The following sections deal with specific issues concerning stability and analysis of T-walls and I-walls. The methods for determination of static and dynamic hydraulic actions acting on the flood walls are presented. Hydrostatic force is deduced from the water levels corresponding to the different design situations, and dynamic forces are estimated depending on the type of wave loads and braking conditions. For For example, non-braking or pulsating waves, impulsive braking or impact waves, broken waves, post-braking or bore waves. Methods for determination of maximum values of core depth for each type of wave conditions are also given. Methods for assessing the stability of the T-walls as regards their thylumos are reviewed. The section reviews the methods of justification regarding bearing resistance, sliding, overturning, overall stability, structural failure, etc. The main principles for the evaluation of the stability of I-walls is also discussed in terms of hydrostatic and hydrodynamic loads, earth loads, seepage effects, etc. The effect of cracking is discussed as regards the Katrina experience, and a brief discussion on advanced soil structure interaction and finite element methods is proposed. The section 8.10 gives elements on bridge formation processes, soil erodability as function of the soil nature, and actual methods for modeling bridge growth. The bridging process is decomposed into 3 steps: initiation, formation, and widening. The factors affecting size and location of the bridge are identified. For example, variation of the crest level, quality of the surface protection, local focusing of wave action due to wave refraction, etc. This section gives a general form of the erosion equation, given by Hanson in 2005, for example, and points out the relationship between soil erodibility and soil type, density, and water content. The different types of models for modeling bridge growth are also reviewed. Non-physically based and empirical models, such as Froelich and Verhage, semi-physically based analytical and parametric models as implemented in some codes, like dam break, and some physically based models as implemented in wind dam or archive break codes. The principles for the selection of input parameters are also discussed. The flood inundation section provides guidance on how to relate accuracy of modeling results to the end users. It aims to clarify the limitations of existing methods and to explain under which circumstances these methods may be applicable. It focuses on input parameters and data requirements for representative modeling, and on the types of existing models. Do we prefer 2D or 3D models? Do models have to solve the shallow water equations, etc., etc.? The different types of inundation models and modeling approaches are presented. The approach assuming instantaneous bridge hydrograph and propagation in the floodplain, which is the first type of model. The decoupled approach, which is based on the determination of a realistic hydrograph at the breach, followed by a separate calculation and propagation in the floodplain. And finally, the coupled geotechnical and hydraulic analysis. Examples of model outputs, such as maps of depths, water levels, and velocities, are given. It is highlighted that they may be used as inputs for evacuation planning, risk analysis, etc. The use of Monte Carlo methods to estimate the effects of breach parameters and certainties within an inundation analysis is discussed in the last section. Thank you for listening to this presentation. We hope it has given you a flavor of the coverage of Chapter 8 and encourages you to investigate the other chapters of the International Levee Handbook, which each have similar presentations. The complete handbook can be downloaded from the Syria website, the link to which is given on the current slide.